Welcome to the video Help with Physics Problems for Physics 1A. This video covers homework set 4, part 2, which is everything under the heading Work Done on an Ideal Gas. For 1121 students, this video will cover a past exam question and then question 6. For 1131 students, this video will cover a past exam question and then questions 8 to 10. Past exam question. In part A of this question, we have a water bath. There's a container here with a heating element and some power P, and into this container we're adding 0.020 litres of water each minute. Remember, 1 litre of water weighs 1 kilogram. So this implies that the rate that we're adding water at, the change in mass over time, is equal to 0.020 kilograms per minute. In this question, we're asked to find P, the power. So power is the energy required for the unit time. dE dt. And we're told in the question that the amount of water doesn't increase or decrease. So in order for the water we're adding to neither increase or decrease, it means that the amount of water that we're adding each minute must evaporate each minute. So the energy required to do that, energy needed each minute is needed for 2 things. One, it needs to heat the water from the 20 degrees, it's 20 degrees when it goes in, heat water 20 degrees C to 100 degrees C. It needs to be at 100 degrees C to evaporate. And 2, needs to cause the water to change state. Okay, so let's calculate the energy needed each minute. We need to heat the water, so that's given by mCW delta T. And then we need to change the state of this water, so that's given by m times the latent heat of evaporation. Okay, so let's calculate this. Each minute, the mass of water we're adding is 0.020 kilograms. The heat capacity of water is 4.2 kilojoules per kilogram per Kelvin, so this is 4.2 times 1,000. The change in temperature, we're getting it to increase by 80 degrees from 20 degrees to 100 degrees. So that's 80. Plus we need the mass of water that we're changing state of, which is 0.020, plus the latent heat of vaporization of water, which is 2.3 times 10 to the 6. Solving this on the calculator, we get that this is 52,700 joules is needed each minute. So the power is equal to the energy over the time. This is 52,700 over 60 seconds because it's in a minute. Usual units for power is watts, which is joules per second. So we need to divide by the 60, which gives us 879 watts when we solve it on the calculator, which to 2 significant figures is 880 watts. So that is the answer to part A. In part B of this question, we have a cylinder and a rod mounted. Here we've got a rod A, with expansion coefficient alpha A. It's initially got length L0 plus D0. And then we've got a cylinder which surrounds rod A, It's made of material B with expansion coefficient alpha B. It's initially got length L naught, and initially it's all at T naught. Okay, so this is the exam question part B, part 1. We're asked to derive an expression for the length D. So D, by definition, is the difference in the length of rod A and rod B. So it's the length of A minus the length of B. Okay, so the length of A is equal to the initial length of A, which is L naught plus D naught, plus the change in the length of A with temperature. So this is L naught plus D naught. The change in length A is given by the initial length A, L naught plus D naught, plus alpha A, plus the change in temperature, which is T minus T naught. Similarly for length B, it's equal to L naught plus the change in length B. This is the initial length of B, and so that's L naught plus L naught alpha B T minus T naught. Okay, so now we've got to find D, which is equal to this minus this. So we've got L naught plus D naught plus L naught plus D naught alpha A T minus T naught. That's just this term here. And then we've got to subtract off this term, so minus L naught alpha B T minus T naught. Okay, this will cancel straight off. And so we've got this is equal to D naught plus, let's expand these brackets. We've got L naught alpha A T minus T naught plus D naught alpha A T minus T naught minus L naught alpha A T minus T naught. And so let's put these terms with the D naughts together. So this is D naught 1 plus alpha A T minus T naught. And then we'll put these terms with the L naughts together. So this is L naught alpha A minus alpha B T minus T naught. So that's probably the neatest way we can write our answer to this part. In part 2, it says give an expression for the value of the ratio D naught on L naught, which produces the result that D is independent of temperature. Okay, so part 2, D independent of temperature. Okay, so D, what we need to do is we need to separate it into terms that have a temperature dependence and terms that have no temperature dependence. So we can write D as D naught, that's just this term, plus T minus T naught, here's our temperature dependence. We've got D naught alpha A plus L naught alpha A minus alpha B. Okay, so this term is independent of temperature. This term has the temperature dependence. So this term must disappear for it to be independent of temperature. So we know that D naught alpha A plus L naught alpha A minus alpha B is equal to 0. So let's give ourselves some more space over here. So we've got D naught alpha A is equal to L naught alpha B minus alpha A. I've just switched around the order of these to make up for that negative sign. And we're asked in the question to find D naught on L naught. So D naught on L naught is equal to alpha B minus alpha A over alpha A. So this is equal to alpha B over alpha A minus alpha A over alpha A, which is minus 1. And so that's the answer to this question. Okay, we're now up to problem 6 for 1121 or 8 for 1131. In this problem, we've got a PV graph. Here's our V, here's our P. This is in kilopascals. and this is in meters cubed. And we've got a cycle. We've got the point here, 20, here's 5, here's 2, here's 8, and points A, B, C, and D. The gas goes from A to C, expanding, and then it has a choice to get back to A. It can go around path 1, which is from C to B and B to A, or it can go around path 2, which is from C to D and D to A. That's 2. The question asks us to calculate the work needed for these 2 cycles. So A to C to B to A, that's cycle 1, or from A to C to D to A. Okay, so both of them contain A to C. Okay, so work done A to C. Well, the gas is expanding, which implies that the work is done by the gas, which means that there's negative work done on gas. The question asks us about the work done on the gas. So this will be negative. So the work done from A to C is equal to minus the integral of P dot dV, which is just the area under this curve here. So it's a trapezium. So it's equal to get the area of the trapezium, we take the average of the 2 heights. So that's 20 plus 5 on 2. And then we times it by the width of the trapezium, which is 8 minus 2, which is 6. Doing that in our heads or on the calculator, and we end up with minus 75. Now, we would say joules because that's the units for work and energy, except that this is kilopascals, so we need to times it by 1,000, so that's kilojoules. Okay, now we have a choice. We need to calculate both. We can go from one. We'll start with path 1. So path 1, from C to B, there's no work as volume does not change. So now we need to calculate the work from B to A. This is a compression, so it's a positive work, and it's equal to the area under this rectangle here, P dot dV, which is just calculating the area. It's 20 times the width, which is 8 minus 2 times 6, so that's 120, and again it's kilojoules because of the kilopascals, which means that the work for path 1, which includes going from A to C and then back, well, from C to B and B to A, so we just sum all the works to get the total work. It's 120 minus 75, which is equal to 45 kilojoules, and it's positive because there's positive work here, which is larger than this negative work. Okay, path 2, from C to D. To get the work, we have to work out the area under here. So it's a positive area because it's being compressed. So that's 5 times 6, which is 30 kilojoules. And then from D to A, there's no work done as the volume's not changing. So work around path 2 is equal to 30 minus this 75, which is equal to minus 45 kilojoules. Okay, so that's the answer to this problem. Problem 9, which is for 1131 only. In this problem, we have a thin tube. We can assume it's got surface area A, and initially it's sealed at both ends. In the middle, length D here, which is equal to 10 centimeters, it's filled with mercury. And then let's let the tube have a length L, which is 1 meter. It's initially on its side, and we have an equal length here, so this is L minus D on 2, and here L minus D on 2. And then we turn it up so that it's vertical. This Mercury is going to move down a little bit. Let's let this length is now L minus D onto plus X, and this is L minus D onto minus X. We've got to work out what this X is by how much it's moved. The downwards force of the Mercury is given by mg, which is equal to rho times d times the area. This gives us the volume times g. And the pressure difference between these two, if we call this P1 and this is P2, P1, which will be at the higher pressure, minus P2, is equal to the force over the area caused by this. So it's equal to rho dAg over A, which is just equal to rho dG. Okay, the question asks us to find X by how much this Mercury moves when A, it's isothermal, and B, it's adiabatic. For an isothermal process, we know that PV is constant. So P0 V0 is equal to P1 V1. Okay, so let's consider this one here. Initially it's at P0, which is atmospheric pressure, and it's got volume V0, so P0, and V0 is L minus D over 2 times the surface area. That gives us the volume here. Then it's down here. Finally, the pressure P1, which we don't know, and the new volume is given by L minus D over 2 minus X times A. The surface areas will cancel out. Let's call this equation 1. For this second half here, we've got P0 L minus D over 2A, same. This is at the same pressure and volume as this one, is equal to P2 L minus D over 2 plus X A, and once again our A's will cancel out. Okay, now we've said that the difference between P1 and P2 is given by rho dG. So P1 minus P2 is equal to rho dG, and this is equal to, we can rearrange equation 1 to get P1, and so this is P0 L minus D over 2. Now P1 is 1 over L minus D over 2 minus X, minus P2, we have 1 over L minus D over 2 plus X, and we've got to solve this. Okay, so we've got rho dG is equal to P0 L minus D over 2. Now we want to solve this. Let's put a common denominator, L minus D over 2 minus X, L minus D over 2 plus X, L minus D over 2 plus X minus L minus D over 2, and then plus X because we've got negative, negative. Okay, so these cancel out and we've got 2X on the top. Now we can make an approximation because we know that X is less than L minus D over 2, and it should be quite a lot less. X is by how much it moves, and it's only going to move by a small fraction of this length here. So that tells us that this is small compared to that, this is small compared to that, so we can just ignore these. Okay, so we've got P0 L minus D over 2. On the bottom, we've got L minus D on 2 times L on D on 2, so that's L minus D over 2 squared, and on the top, we've got 2X. Okay, so that will cancel. Now what we're trying to do is find X, so X is equal to, here we've got rho dG, and then we've got this L minus D over 2. We've got to divide by this 2, so get rid of that 2 and make that a 4. And we've also got to divide by P0. Okay, now we need to look up the density for Mercury. In kilograms per meter cubed, it's 13,534 times D, which is 0.10, times G, which is 9.8, L minus D, that's 1 meter minus 10 centimeters, so that's 0.90, all over 4 times, initially it was at atmospheric pressure, so that's 1.01 times 10 to the 5. Solving this on the calculator, we get 0.0295 meters, which is equal to 2.95 centimeters. So that's how much it moves in the isothermal case. Okay, now we need to do it for the adiabatic case, which is where PV to the gamma is constant. And we're told that in this case, gamma is equal to 1.40. Okay, so we do this in a very similar way. We've got P naught V naught. The initial volume is L minus D over 2 to the gamma A to the gamma is equal to, for 1, remember 1 was the one down the bottom. We've got P1 V1, P2 V2, and P1 minus P2 is equal to rho GD. And so P1 is given by P1, and then we need V1 to the gamma, which is A to the gamma, times this new length here, which is the L minus D over 2 minus X to the gamma. And we've got P naught L minus D over 2 to the gamma A to the gamma is equal to P2, we're considering this part, L minus D over 2 plus X to the gamma. Okay, the A to the gammas cancel out. And then we've got P1 minus P2 is equal to rho GD, which is equal to P naught L minus D over 2 to the gamma. That happens in both these ones. And then we've got 1 over L minus D over 2 minus X to the gamma minus 1 over L minus D over 2 plus X to the gamma. Okay, let's rearrange this. So we've got P naught L minus D over 2 to the gamma. Let's give this a common factor. L minus D over 2 minus X to the gamma. L minus D over 2 plus X to the gamma. And we've got L minus D over 2 plus X to the gamma minus L minus D over 2 minus X to the gamma. Okay, now we can make the same approximation as last time. This is small compared to that, and this is small compared to that. So those x's we can ignore. So one of these terms will cancel with that term there. So let's rewrite this. We've got P naught over L minus D over 2 to the gamma. Now, to deal with this, we actually need to take out L minus D over 2 as a common factor. So we've got L over D over 2 to the gamma times, this is 1 plus X over L minus D over 2 to the gamma minus 1 minus X over L minus D over 2 to the gamma. Okay, now this is small, which tells us that we can actually do a Taylor series expansion of this thing. So if we let this equal, say, A, then we've got 1 plus A to the gamma minus 1 minus A to the gamma. And when we do a Taylor series expansion of this for A is less than 0, we get that this is approximately equal to 2 gamma A. Okay, so we can write this as, this and this will cancel out. So we've got P naught, and then we've got 2 gamma and A, which is X, over L minus D on 2. So let's put the 2 up there. Okay, now this is all equal to rho G D. We just need a little bit more room. So let's start a new page. Okay, so the last line we had rho G D is equal to P naught times 2 gamma times 2x over L minus D. Now what we're trying to find is x, so let's rearrange this. We've got x is equal to rho G D. Now this L minus D comes up the top and we'll have divided by this 4 gamma P naught. Now we need to evaluate this. The only difference between this x and the x we had in part A is this gamma here. So what we can actually do is say that this is 2.95 over gamma centimeters. So this is 1.4. So solving that on the calculator, we end up with 2.11 centimeters. Okay, so it shifts less in the adiabatic case. Now the question also asks which assumption is more reasonable. Well, we can assume that it happens quickly, that we turn it from its horizontal position to its vertical position quickly. So it happens quickly, which implies there's no time for heat to flow, which implies that it's isothermal. So the adiabatic approximation is the better one. Over time, it's reasonable to assume that it will reach thermal equilibrium. So this implies that over time, it will approach part B. So it'll start off moving 2.95 centimeters and then it'll slowly move up until it's only displaced by 2.11 centimeters. Problem 10. In this problem, we have 1.35 moles of oxygen at 11.0 degrees C. And we're told that its volume doubles, so it goes from V to 2V. And we're asked, how much heat do we need? And we're told that P is constant. Okay, this is very important. It tells us two things. With the ideal gas equation, we've got PV is equal to nRT. This is not changing, this is not changing, and this is not changing. So this tells us that V over T is equal to constant. So V naught on T naught is equal to V1, which is 2V naught on T1. And so T1 is equal to 2V naught over V naught times T naught, which is 2 times T naught. So this is, the temperature is in kelvins, so this is 2 times 11 plus 273, which tells us that the new temperature is 568 kelvins, which is 295 degrees C. Okay, so we've got the change in temperature now. Now the heat energy is equal to the specific heat, which in this case is the specific heat at constant pressure. So this is the second time we're using this. P is constant times the number of moles times the change in temperature. Okay, so Cp, we're told we're allowed to assume it's 7 over 2R. Now that makes sense because it's O2, which has 5 degrees of freedom, 3 translational ones and 2 rotational ones. So F is 5. So this is F plus 2 on 2R, and then the number of moles we're told is 1.35. And the change in temperature is the final temperature minus the initial temperature. We can do that in degrees C, and that gives us R is equal to 8.314, 11,156 joules, which is equal to 11.2 kilojoules, to 3 significant figures. This is the past exam question. I recommend that when answering questions like this, you write everything that you know onto the diagram. So it says that the diagram shows a cyclic process, and that as the gas goes from states A to B, 1,515 kilojoules of heat energy enters the system. So we can write here Q equals 1,515 kilojoules. And then as the gas goes from C to D, 704.5 kilojoules of heat energy leaves the system. So here we can put Q is equal to minus 704.5 kilojoules. The process from B to C is adiabatic, so this is adiabatic, which tells us that Q is equal to 0. And from D to A is isothermal. So here's isothermal. So the change in internal energy is equal to 0. And the volume at C is 5.79. So here volume is equal to 5.79 meters cubed. Okay, so looking at the questions, first says calculate the work done as it goes from A to B. So to do the work, remember we just need to find the area under the curve. So what we need to do is find this volume in here, and that comes about because work is equal to minus the integral of P dot dV. In this case, P is just constant, so it's when we do the integral, we're just finding the area of a rectangle. So this is equal to minus. It is a minus because it's expanding, and so work is being done on the work being done on the gas is negative. And so the pressure is 3 atmospheres. So we should write that as 3.00 times 1.01 times 10 to the 5. That's just converting from atmospheres to pascals times dV, or the change in volume. So it's going from 1 to 3 meters cubed. So the change in volume is 3 minus 1. We can now solve that on the calculator. And when we do that, we get minus 6.06 times 10 to the 5 joules. Which we can write as minus 606 kilojoules if we want. Now part 2 then asks us what is the change in internal energy as it goes from state D to state A. That's easy because it's isothermal. So that tells us that the change in internal energy is equal to 0 because the temperature doesn't change. Now part 3 asks us what is the change in internal energy as the gas goes from B to C. So the change in internal energy from B to C we need to find. Now there's a couple of ways we can do this. Probably the easiest way is to consider the cycle, and we know that the change in internal energy around the cycle is 0. So that means that this is the negative sum of the other internal energies. So the internal energy from A to B plus the change in internal energy from C to D plus the change in internal energy from D to A, which we already have. We know from D to A it's 0. So we know this one's 0 already, so we just need to work out these two. And so the change in internal energy from A to B, we can use the first law of thermodynamics, that the change in internal energy is equal to Q plus W. This is from A to B and A to B. We've worked out the work from A to B up here, and we're told the Q. So we've got 1,515 kilojoules minus 606 kilojoules. And solving that, we end up with 909 kilojoules. And then the change in internal energy we need along here now from C to D. Again, it's Q plus W. We've already been given the Q. It's minus 704.5. And then what we can do is the same thing as we did up here. It's the integral of P dot dV, but the P is constant, so it's just the area of this rectangle here. And so that is equal to the pressure, which is 1.01 times 10 to the 5 pascals. So we'll just divide that by 1,000 because we want to end up in kilojoules, as this is in kilojoules, and then times the change in volume, which is equal to 3 minus 5.79, and we should actually have a negative here. In the end, because it's being contracted, we should end up with a positive value for the work done in this case. So if we multiply that by 5.79 minus 3.00, that cancels off our two negative signs, and we end up with minus 422.7 kilojoules is the change in internal energy from C to D. And so then the change in internal energy from B to C is equal to negative 909 minus 422.7, which gives us minus 486 kilojoules. So that's the end of the 1121 question. The 1131 question then has write down an equation relating P and V as the system goes from B to C. So B to C is adiabatic, so we know that PV to the gamma is equal to a constant, and we're asked to calculate as many of these constants as possible. Okay, so P and V are variables, so we can't calculate them, but gamma, that's a constant, and it is equal to Cp on Cv, and we know that Cp is R plus a half Fr, and Cv, that's R plus Cv, and this Cv is a half Fr. So all those R's cancel out, and we're told at the start that this is a monotonic ideal gas, and because it's monotonic, we know that F is equal to 3. So here we've got 1 plus 3 over 2 divided by 3 over 2. So that's 5 over 2 over 3 over 2, which is equal to 5 over 3. So we've worked out what the gamma is. We can also work out what the constant is, as we know point B, for example, has to obey this equation. So point B, we've got 3.0 times 1.01 times 10 to the 5 times the volume, which is the 3, to the gamma, which is the 5 on 3, is equal to this constant. So now what we can do is we can just enter that into the calculator, and we find that this constant is equal to 1.89 times 10 to the 6, and the units for the constant is the pressure, which is the pascals, times the meters cubed to the 5 on 3. So that is pascals meters to the 5. So we've got an equation, PV to the 5 on 3 is equal to 1.89 times 10 to the 6 pascals meters to the 5. And so that's answer part 4. So we've now answered this question, but I said before that there was a couple of ways that we could do question 3. The other way to do question 3, which we can do now just to check, is to use this equation here for relating P and V to calculate the work done in this case. And we know that because the heat is 0, the change in internal energy must be the work done from B to C as well. So the work from b to c is equal to minus the integral of p dot dv, and that's going from vb to vc, and p here is equal to this divided by v to the 5 on 3. So we can write this as minus 1.89 times 10 to the 6 times the integral of v to the minus 5 on 3 dv from vb to vc. And so this is equal to 1.89 times 10 to the 6 times, now we need to integrate this thing, and when we integrate it we end up with v to the minus 2 on 3, and then we need to multiply that by minus 3 on 2, and then we're going from VC here is 5.79, this is 3.00. So now we enter this into the calculator and we end up with minus 483 kilojoules. So 483 is pretty much the same as 486, just with the number of significant figures we've kept everywhere will be that very, very small discrepancy there. So now we can be happy because we've calculated this 2 ways and both our ways agree, suggesting that we've solved this correctly.